in this question, we are given a one-dimensional potential and we are asked to plot the phase space trajectory of a particle moving in this one-dimensional potential. So what we'll find is we'll find the maxima and the minima points for this one-dimensional potential. So the given function is, we are given this is the function. So how do we find the stationary points? We set the first derivative equal to 0 and we find the corresponding point, solve for x. So the first derivative is set to 0 and we solve for the points and check that we get, so this is nothing but minus x plus x cube. So check that you get x is equal to 0 plus 1 minus 1. So it has 3 values. So there are 3 stationary points. So from these points, we have to find out which point is a maxima, which point is a minima. So we will do the second derivative test. So check that the second derivative is actually negative is equal to minus 1 or it is less than 0, negative at x equals 0, okay, at x equals 0. And therefore, what does this mean? This means that it is a maxima, okay, at this point. This point is a point of maxima, okay, so this is maxima. And we have the second derivative greater than 0, that is, it is positive at x is equal to plus or minus 1. Therefore, this means that this is a minimum. Okay, so this is what it means. So now, so the potential looks something like this. Okay, so it looks something like this. So you have a maxima at, so this is what your potential looks like. So you have a maxima at 0, a minima at plus or minus 1. So this is plus 1, this x is equal to 1, this x is equal to minus 1, this is x is equal to 0. Okay, so that's what we have. Now we have to solve for the phase space trajectory. That means you have to find the relationship between the generalized coordinates. Here we are taking x and the conjugate momenta p. So let's write out the Hamiltonian. The Hamiltonian is p square by 2m, the kinetic energy and the potential energy, the sum of the kinetic and the potential energy. So this is our Hamiltonian, and Hamilton's equation says x bar is equal to dh by partial of derivative of h with respect to p, and p bar is given by this. Now we solve for x bar. X bar is nothing but p by m. So this is the Hamiltonian. You have to differentiate it with respect to p. So you get p by m, x bar. And p bar you get x minus x cubed. Now let's divide p bar by x bar. Let's divide p bar by x bar and you get x minus x cubed by p by m. Now we take all the p's to one side, x's to the other side. Okay, and what we will do is we will solve this equation by means of the separation of variables method. So this is p dot is nothing but dp by dt. X dot is nothing but dx by dt. So this just becomes dp by dt. So this just becomes dp by dt. Sorry, dx, dp by dx. And the m will go to the numerator, obviously. So now bring all the x terms to the one side and p terms to the other side. So once you do that and you integrate, you will get your phase space trajectory, the equation for your phase space trajectory, from which you can infer the details. So so when you, this is integration by separation of variables. So you bring all the x terms to the one side and p terms to the other side. So this is obtained from this equation, rearranging this equation. So now what you have is the solution is p square by 2 is equal to m x square by 2 plus minus x to the power 4 by 4 plus a constant, obviously an integration constant, but let's take the constant to be 0 for the sake of simplicity. So now what you have is at x is equal to 0, p is equal to 0, and at x is equal to plus or minus 1, p is equal to plus or minus m by 2. So we see that the momentum is taking a constant value at plus or minus 1. So therefore from these information we can plot out the phase space trajectory.